So thank you for the introduction, and also thank the organizers for the kind invitation to contribute to this very interesting and informative conference. So as advertised in the title, this presentation will be about S matrices for quantum-deformed superstrings, and this is based mainly on two papers that I wrote together with Stijn van Tongeren and Yannik Zimmermann, and also some earlier work together with Ben Hoare. Okay. So the reason why this conference series exists was the discovery about 20 years ago that some theories that are important in the context of ADS-CFT are also integrable. So the prototypical example is the duality between type 2B superstrings on ADS5 cross S5 and on the gauge side n=4 super Yang-Mills in 4-dimensional Minkowski space. So these theories are integrable in the free strings and planar graph limit. And the integrability machinery has been applied in order to obtain the string spectrum or also anomalous dimension of operators on the CFT side. We have also seen during this conference that the integrability machineries can be applied in order to obtain structure constants and also higher point correlation functions. Also, we have seen that in the talk before mine. And this prompts then the question whether we can apply this to other superstring theories. So are there other superstring theories for which the integrability program can be applied? So of course, the answer is positive, and we can start by looking at lower dimensional ADS-CFT setups. For instance, we have seen during this conference the case of ADS3 cross S3 cross D4, but there are also other lower dimensional examples. These theories have less supersymmetries than ADS5 cross S5. They feature new features, and they are therefore very interesting to study in their own rights, but they are still the most supersymmetric in their respective dimensions. So we might want to go beyond that and look at theories that break the supersymmetries. A way to do this is look at integrable deformations of ADS-CFT setups. So an example that you might be familiar with are TST transformations. So these are a combination of T-duality, shift, and T-duality. So you can do that whenever your your background has two isometries. This will map you from a string theory to a string theory, and in some cases the dual is known. So for instance, we have seen during Anne Spiring's talk cases of beta deformed n=4 super Yang-Mills, and this is in some cases this theory is integrable, and it is dual to Lunin-Maldacena background. So when you take TST transformation on the sphere of ADS5 cross S5, so on this 5 sphere. You can do other types of integrable deformations. So I believe we will hear more about TT-bar deformations this afternoon. You can also do more general current deformations. And other types of integrable deformations are quantum deformations, for which, as we will see, the symmetry algebra of the theory will be promoted to a quantum group. And examples are eta deformations and lambda deformations. And you can also do some more general types of integrable deformations that are called Yang-Baxter deformations. So in this talk, I will focus on quantum group deformations and more precisely eta deformations. So the plan is the following. I will first present to you the deformed model, and then we will analyze in more detail the quantum group symmetry of these theories. And I will then look at the scattering theory of the deformed model. So we will look at the worldsheet S matrices, and I will finish with some conclusions and open problems. So let's start with defining these integrable eta deformations. If the computer cooperates. Okay, so on the string side of the duality, as you might know, classical integrability arises from the formulation of the Green-Schwarz string as a sigma model on a special space, namely a semi-symmetric space. And the eta deformation will basically be a deformation of the semi-symmetric space sigma model. So let me start by defining the undeformed theory, so the semi-symmetric space sigma model, and this is a sigma model on the supercoset G mod H, where the supergroup G, so the Lie algebra of the supergroup G that I will denote by this Gothic G, here has a Z4 grading, so you can decompose it into four subspaces, G0, G1, G2, and G3, and G0 and G2 have even grading, and G1 and G3 have odd gradings. So the even grading generators, so this would be your bosonic generators, and in G1 and G3 you will find your fermionic generators. So this is compatible with the Lie bracket, meaning that G0 will be a subalgebra, and this is identified with the Lie algebra of the group H. So the action of the semi-symmetric space sigma model, the action is the following. So you have different terms that appear. You have an overall factor, which is the string tension. Then you do an integration over a two-dimensional space. So this would be, in the case of string theory, this would be your worldsheet coordinates. Then you have some quantities that appear. So the Weyl invariant metric on the worldsheet, you have the antisymmetric tensor. And then you take the supertrace of two left invariant Maurer-Cartan forms. So this G inverse dG, where G is a supergroup valued field. So G belongs to this supergroup G that I have introduced previously. And in the middle, you put a projector. So maybe some comments about the properties of this theory. So first, the fact that you use the left invariant Maurer-Cartan forms, G inverse dG, will ensure that you have a global left-acting G symmetry. And this projector that you insert will ensure that you have a local right-acting H symmetry. You also have worldsheet diffeomorphism. So this action is invariant under reparametrization of the worldsheet. And the specific form of the projector also ensures that you have a fermionic kappa symmetry, meaning that this will ensure for you that the number of bosonic degrees of freedom is the same as the number of fermionic degrees of freedom. Furthermore, this theory is classically integrable in the sense that you can recast the equations of motion as a flatness condition for a lax connection. So this is the undeformed model, and with this you can describe Drinfel'd superstrings on various backgrounds. For instance, for ADS5 process 5, the supercoset that you need to consider is PSU 2,2/4 over the homotopy of the 5-sphere and the 5-dimensional ADS space. So now let's look at the deformed theory. So there will be two new ingredients to define the deformed theory. One ingredient is a real parameter eta that will be the strength of your deformation, and with eta equal to 0 corresponding to your undeformed theory. And then by tuning on eta, you will go away from the undeformed theory. And the second crucial ingredient is a so-called Drinfel'd operator. So this is a linear map from the Lie algebra, the symmetry algebra G to itself, and it acts as follows. So you take your symmetry algebra G, you decompose it into Cartan elements H, positive and negative roots E plus and E minus, and this Drinfel'd operator will annihilate the Cartan elements and multiply with plus or minus I, the positive and negative roots. Important properties of these operators are the following. So first, it is antisymmetric with respect to the supertrace, and it satisfies the so-called inhomogeneous classical Yang-Baxter equation that takes this form. So now that we have defined the two crucial ingredients for our deformed theory, we can write down the action, and it looks as follows. So the difference with respect to the undeformed case is that you now insert this non-trivial operator between the two left invariant Maurer-Cartan forms. So you see that this operator R that I introduced, this Drinfel'd operator, appears in the denominator of this non-trivial operator here. You also have the deformation of the projectors. So what are the properties now of this deformed action? So in general, the global left-acting G symmetry will be broken by the insertion of this operator. And if you choose the Drinfel'd operator, as I do in this talk, then this will be actually broken down to just U1s. The local right-acting H symmetry is still there, and so are the worldsheet diffeomorphism and also the fermionic kappa symmetry. Furthermore, this operator, this Drinfel'd operator, has been chosen in such a way as to ensure classical integrability, meaning that again, you can recast the equations of motion as a flatness condition for a lax connection. Furthermore, as I will expand on later during the talk, this theory has actually a quantum group symmetry. So recall that the global left-acting G symmetry is broken, but you actually have a hidden quantum group symmetry where the parameter of the quantum group, so this Q, is real and is related to the deformation parameter eta and the tension in this way. So this model was introduced by Delduc, Magro, and Vicedo, and this builds up on works done by Klimchik for the principal chiral model. So one can then ask whether these theories are unique. So how unique is this Drinfel'd-Jimbo operator that are introduced? And in the case, there is a question in the audience.
Sorry, can you go back a second to the formula for Q?
Yes.
I was just wondering. No, okay. Sorry, I was just wanted to understand. This is just it's a formula that is valid for
it's
always
semi-classical.
real. Sorry.
It's semi-classical.
Okay.
Yes.
And it's always valid for real Q. I mean, if you wanted to do Q, which is a phase, you would have to start from a different point, or.
So for these theories, Q will always be real. There are other deformations for which Q is actually a root of unity. These are these lambda deformations. And there you start actually not from the theory itself, but you start from the non-abelian T-dual and you deform this non-abelian T-dual. But in these eta deformations, this parameter Q is real.
Okay, thanks.
Okay, then we ask whether this operator R that we introduced is unique, and this will actually depend on this symmetry algebra of the undeformed theory G. So in the case when G is a complex semi-simple Lie algebra, or you consider a real form, for instance, so SL4 and the real form SU4, then so the compact real form, then you actually have a unique Drinfel'd-Jimbo operator, and this will define for you a unique eta deformations. In the case when you take a non-compact real semi-simple Lie algebra, for instance, SU2, 2, which is important in the context of ADS5, then you actually can have different Drinfel'd-Jimbo operators, and these will be different analytic continuations of this unique R that you define for the compact real form. The eta deformations are then different, but however, they are related by a complex field redefinition. When G, and this is the case that will interest us, when G is a complex semi-simple Lie algebra, so if you consider the formation of superstrings, then for instance SL2/2, then you can have different Drinfel'd-Jimbo operators that are associated to different Dynkin diagrams. And there, the resulting theories are really different. So you get different eta deformations that are no longer related by a complex field redefinition. So the best way to look at these different eta deformations and characterize how different they are from each other is to look at the backgrounds that they generate. So in order to obtain the background, you start from this concept model that I introduced. You choose a specific parametrization, you expand to quadratic order in the fermions, and you compare to the general formula of the Drinfel'd string. And this allows you to obtain the metric, the B-field, and also the Ramon-Ramon fluxes. What you end up with is that these different theories, so if you take the Drinfel'd-Jimbo operator to be associated to different Dynkin diagrams, then these theories have different, same metric and B field, so up to complex field redefinition, because again, you can choose different R matrices because of the non-compactness of SU2, 2, so for ADS5. And what you will see is that you will actually have different Ramon-Ramon fluxes, and an explicit formula for the Ramon-Ramon fluxes has been obtained by Borsato and Wolf in 2016. So let's look at specific examples of deformations. So in the case of ADS5 cross S5, the symmetry algebra is given by PSU2, 2/4. So this is a rank 7 superalgebra that has actually many different Dynkin diagrams, and here I will focus on 2 of them. So one is the distinguished Dynkin diagram. So you have 6 bosonic simple roots. So here the bosonic simple roots are denoted by a circle, and then you have 1 fermionic simple root. So this is the circle with a cross. So this is the original eta deformation as was studied by Arutyunov, Borsato, and Frolov in 2013 and 2015, and they obtained the background. So the background in this case depends on this parameter eta that I introduced, and you have a 1 form, a 3 form, and a 5 form. So you have all of them turned on. An interesting property of this background is that it actually does not solve the supergravity equations of motion, and this was quite a puzzling feature at the time. Another possibility is to look at the fully fermionic Dynkin diagram, so where you have all your 7 simple roots fermionic, and in this case, the bosonic background is supported by a Ramo-Ramo 3 form and a 5 form, and in this case, the background solves the supergravity equations of motion. So by considering 2 different eta deformations that are constructed out of 2 different Drinfel'd-Jimbo operators, so with these 2 different Drinfel'd-Jimbo operators associated to different Dynkin diagrams of the original symmetry algebra, you actually generate different types of backgrounds that have quite different properties, in the sense that some of them will be solutions to the supergravity equations of motion and some of them are not. And in fact, the only way to build eta deformations that are supergravity that give rise to backgrounds that are supergravity solutions is to consider this fully fermionic Dynkin diagram. All the other will give rise to are not supergravity solutions. Another example is the case of ADS 3 cross S3 cross T4. So in the case of pure Ramo-Ramo fluxes. So in this case, as was highlighted by Dennis in the previous talk, the symmetry algebra is given by 2 copies of PSU 1,1/2 that I will also denote by left and right. And since you have this nice structure, you can actually define a 2-parameter deformation. So you can deform the 2 copies in different ways. And this will give rise to a 2-parameter deformation. So instead of having just one deformation parameter eta, you now have eta left and eta right. Each gives the strength of deformation in each copy. So now let's look at some different eta deformations in this case. So you can build a deformation out of the distinguished Dynkin diagram of PSU 1,1/2. So you take the distinguished Dynkin diagram in both copies. And in this case, the background is supported by a 1-form flux, a 3-form flux, and a 5-form flux. And again, it doesn't solve the supergravity equations of motion. You can also look at this kind of mixed Dynkin diagram. So you take again the same Dynkin diagram in both copies, and you look at the background that this R matrix generates, or this operator R generates, and you see that you again have a 1-form flux, a 3-form flux, and a 5-form flux. And again, it doesn't solve the supergravity equations of motion. And similarly to what happens in the ADS 5 cross S5 case, if you want to have a background that solves the supergravity equations of motion, then you need to look at the fully fermionic Dynkin diagram. So you choose the fully fermionic Dynkin diagram for both PSU 1,1/2 copies. In this case, the background is supported by a 3-form flux and a 5-form flux, and it solves the supergravity equations of motion. Perhaps an interesting feature in this case, or an interesting observation, is that these 2 backgrounds that I have presented here for the distinguished Dynkin diagram and this mixed Dynkin diagram, they're actually not independent from each other. They are actually related by deformation parameter dependent TST in the torus direction. So this is just a nice observation that I will not expand upon here. Good. So now that I have defined that we have seen some of these deformed theories, let me expand more on the quantum group symmetry that they have. So I have told you that these theories, so they break the symmetry algebra of the undeformed theory, and you are left just with U1s, but you have a hidden quantum group symmetry. So we have seen these quantum groups in several talks now, but let me give you a brief review of how they are constructed. So let's start with the Lie superalgebra, and again decompose it into Cartan elements, positive and negative roots. So this will be the same decompositions as the one that we used for the operator R. And so this Lie algebra is defined in terms of commutation relations, and we have the Cartan matrix that appears here. And you can promote this Lie superalgebra to a Hopf algebra by adding to the theory this coproduct. So here you take the trivial coproduct So this coproduct will allow you to go from the Lie superalgebra to the Hopf algebra, and it's a Lie algebra homomorphism. Now, if you want to define the Drinfel'd type quantum group that I will denote by GQ, then you deform the commutator between a positive and negative root in the following way. So instead of having just a Cartan element h that appears, you actually have powers q to the h. You also have a deformation of the coproduct, and this will be important when we will look at the scattering theory of these models. So if you take q going to 1, then you recover the undeformed Lie algebra or undeformed Hopf algebra. So as I have mentioned already, this decomposition that you do for the Lie superalgebra is the same as the one that you choose for the Drinfel'd-Jimbo operator R. And I have told you that you can have, for superalgebras, you can have different Dynkin diagrams. So in principle, you can actually have different types of Drinfel'd type quantum groups. You do not have only one type of Drinfel'd type quantum group, you have several types of Drinfel'd type quantum group, depending on which Dynkin diagram you choose. So how are these different quantum groups related? So let us start from this Lie superalgebra G and construct two Drinfel'd type quantum groups, one that is constructed out of one Dynkin diagram and the other one constructed out of another Dynkin diagram. Then what happens is that the Q-deformed algebras are isomorphic, so you can find a Lie algebra isomorphism. However, the Q-deformed coproducts are related by a twist, so this F. And this twist needs to satisfy, so this is a Drinfel'd twist, so it will satisfy a co-cycle condition that involves the coproduct, and that reads as follows. So for example, if you look at SL2/2, then we have the distinguished Dynkin diagram, and we have the fermionic Dynkin diagram, and you can actually go from one Dynkin diagram to the other by doing a so-called generalized Weil reflection in the fermionic root. So the effect of this generalized Weil reflection will be to change the nature of the two adjacent nodes. So here you have two adjacent bosonic nodes, and these will become two fermionic nodes. So this generalized Weil reflection allows you to go from one Dynkin diagram to the other, and in fact, this twist will be the explicit formula for this twist actually depends on which type of Weil reflections you need to do in order to go from your Dynkin diagram 1 to your Dynkin diagram 2. So in this case, in this explicit example, it reads as follows. So you see that when you take Q going to 1, so in the undeformed theory, you actually recover the identity, and it involves the positive and negative roots that on which you do the generalized Weil reflection. So now that we have studied the symmetries of these theories in more detail, we can now go to the part where we look at the scattering theory and obtain the worldsheet S matrices. But perhaps there are questions before we do look at this.
One question online.
Yeah, hi Fiona. Just maybe one precision is regarding this Weil reflection. When you do the deformation, assuming that the deformation affects just the positive negative e's. My point is that in this Q-deformed case, when I'm reflecting and obtaining the full cross, you're not saying anything about solving Sugra, or you do, like in the previous case, when you said that the two etas do not solve, but the full cross does.
Sorry, I didn't understand. When I looked at the two etas, what?
So the previous, as you have been shown if you remember, three Dynkins with a separated one and the mixed one.
This one?
Yeah, with the foot. Yeah, exactly. But can you say something like this when you look at the Q deformation?
Yeah. Yes. I mean, I'm not sure exactly what the question is, but here you have these different. I mean, you choose the R matrix based. So you have this Drinfel'd-Jimbo operator that depends on the choice of Dynkin diagram, and the theories that you build using this operator will have a Q-deformed symmetry, and this Q deformation will be exactly the same as it will be the one that you build using this same Dynkin diagram.
Yeah, exactly. So what I mean is that this is the supergravitational background, but as you say here, it is not SUGRA. You do in the Q-deformed case the generalized wire reflection, and you get to the 3 crosses, which is affecting the first diagram. And then it is still SUGRA, right? Like as a very last you show with the 3 crosses, it is SUGRA.
Yeah, this one is a supergravity solution.
Yes, so I'm saying is that there is a similar structure when you talk about the Q-deformed case algebras for the R matrices.
Yes.
So the Q deformation, for example, the Q deformation affects this argument or not?
So Anton, maybe we can postpone the question to the end of the talk, and we wait for Fiona to go on.
Yeah, I would be happy to answer at the end.
Yeah, sure.
So let us now look at the scattering theory of these deformed models. So I defined the eta deformation at the level of the semi-symmetric space sigma model, and there we have reparametrization invariance. So we first need to remove these redundancies, and we will do this by fixing Lycon gauge, and also we have to choose a kappa symmetry gauge. So this will allow you to go to the gauge fixed model where the theory is defined on a cylinder. And then in order to have good asymptotic states, we will then take the radius of the cylinder to go to infinity. So this is the decompactification limit, and we will end up with a massive two-dimensional quantum field theory that is defined on a plane, and for which we can explore the S matrix. So this is the worldsheet S matrix. And in order to find this S matrix, we will make 2 assumptions. So one is that the Q-deformed symmetry that we have seen actually extends to the quantum theory as well. And the second is that classical integrability also extends to the quantum theory. And if you ask for quantum integrability, this will actually impose constraints on the scattering matrix of the theory. So one constraint is that you cannot have any particle production. The second constraint is that the set of incoming momenta is the same as the set of outgoing momenta. And the third property is the property of factorization, meaning that if you have an n-body scattering event, this factorizes into a sequence of 2-body scattering events. So the crucial ingredient in the context of quantum integrable system is this 2-body scattering matrix. And consistency requires that it satisfies the quantum Yang-Baxter equation. So this you can obtain by looking at the scattering of 3 particles, and it can be done in 2 different ways depending on which particles scatter first. So either you scatter particle 1 and 2 first, or you scatter particles 2 and 3 first. And consistency requires that the 2 different pictures are the same, and this gives rise to the quantum Yang-Baxter equation. These two-body S matrix can actually be bootstrapped. So this is already the case. So this is the case in the undeformed scenario, where you can actually bootstrap the S matrix using the symmetries of the theory. And here, the Q-deformed symmetry algebra is actually powerful enough to do the same in the quantum-deformed case. So let us look at the case of ADS5 process 5. So in this case, when you fix Lycon gauge, you will have a symmetry breaking pattern. So you start from PSU2,2/4, and you end up with 2 copies of SU2/2. And since you also want to consider off-shell scattering, you need to look at the centrally extended algebra. In the Q-deformed case, so PSU2,2/4 is replaced by its Q-deformed version, and so are the 2 SU2/2 factors. Now, a slight subtlety is that one factor is deformed with Q and the other one is deformed with 1/Q. So now I have also told you that you can have different types of quantum groups depending on which Dynkin diagram you choose for your decomposition of the symmetry algebra. So you can actually have different types of Q-deformed PSU2,2/4. And similarly, you have different types of Q-deformed SU2/2. So you need to understand for each case separately what symmetry breaking pattern you have. So in the case of this distinguished Dynkin diagram, the symmetry breaking is the following. So you start from a Q deformation based on the distinguished Dynkin diagram, and you end up with a Q deformation of SU2/2 that is also based on the distinguished Dynkin diagram, but now of SU2/2. In the case of the fully fermionic Dynkin diagram, the symmetry breaking pattern is the following. So here you have the fully fermionic Dynkin diagram for SU2/2. So you see that you end up with 2 copies of SU2/2 Q-deformed. So it will be sufficient to construct the Q-deformed version of the SU2/2 centrally extended invariant S matrices. And as I have highlighted to you, these different Q deformations are actually related by a twist. And we therefore also expect the S matrices to be related by a twist. So there is a question in the audience.
Yeah, so I'm a little bit confused by one thing, because if I look at your formula before you put a Q, everything looks very symmetric in like the 2 copies of SU2/2. And then also the rows below, they look very symmetric in the 2 copies of SU2/2.
Yes.
So how does the theory know which copy gets a Q and which copy gets a 1/Q?
So if you just look at SU2/2, then you can, I think you can embed them into PSU2,2/4 a bit, I mean, like you want. However, since you have the central extension and you need to have the same central elements in both copies, this will basically fix you how they are embedded into PSU2,2/4. And this, by requiring that the central elements are the same, this will actually tell you that one will be deformed with Q and the other one with 1/Q. So since you have the central elements, the embedding is no longer free. You really have to choose a special embedding. And but perhaps if you remember in the case of, in the undeformed case, when you have these 2 SU2/2 copies, I mean, if you remember, they are embedded into PSU2,2/4 in different ways, in the sense that one will have the S and or the Q and Q dagger in like in upper triangular part and lower triangular part, and it will be the opposite for the second copy.
Okay. Now I was just wondering, like if I put 2 people in 2 rooms and I ask them to do this pattern, whether they would assign in a unique way which copy gets a Q and which copies get the 1/Q, or whether one could say, well, it's the left one that should get 1/Q and the right one should get Q.
Okay. So you ask about the 2. No. Okay. So here I just want to say that one is deformed with Q and one is deformed with 1/Q, but whether you choose the first one or the second one, I think this is irrelevant. It's just a matter of, I mean, it's just a matter that the 2 are deformed in different ways, but which one is deformed in a precise way doesn't really matter. Okay, so these two Q deformation are related by a twist, and therefore we also expect the S matrix to be related by a twist. So here I rewrote the twist in the case of SU2/2 that allows you to go from the distinguished to the fermionic Dynkin diagram, but you see that there is a slight modification, and this is because of the central extension. So you also have the braiding that appears. So let us check this in the case of the fundamental S matrix. And okay. So the fundamental SUQ2/2 centrally extended S matrix in the case of the distinguished Dynkin diagram has actually been obtained in 2008 by Beizert and Korotev, and it satisfies all the properties that you might want from your S matrix, namely braiding and matrix unitarity. It also solves the quantum Yang-Baxter equation, so this is consistent with integrability, and you can also impose crossing symmetry. An important feature that I want to highlight is that you have a bosonic SUQ2 plus SU2Q sub-Hopf algebra. So within your S matrix, you will find 2 blocks that correspond to the SUQ2 invariant S matrix that takes this form. Furthermore, you can, so here we only worked with the symmetries of the theory, but of course, we also need to check that it actually is consistent with the model that we started with, namely eta deformations. So we need to compare these exact results with the perturbative calculations, and with Stijn and Yannik, we showed that this exact S matrix is indeed matches with the three-level expansion of the perturbative, so from a perturbative calculation, if we start from the eta deformation that is constructed using the distinguished Dynkin diagram, and this Q is precisely the one that I highlighted when I studied the Q-deformed symmetry. Then we also looked at the fermionic S matrix. So we constructed it, and again, it satisfies braiding and matrix unitarity. It also solves the quantum Yang-Baxter equation, and the crossing equations are the same as in the distinguished case. The subalpha algebra is no longer there, so this block that you had previously in the S matrix gets replaced. Again, the three-level expansion matches the perturbative calculations if you start from the eta deformation that is based on the fermionic Dynkin diagram. So these two S matrices seem to be not related by a one-particle change of basis, and this remains true at the three-level case. And perhaps also one comment is that if you check with the perturbative results, here you see that you really need to take one copy deformed with Q and the other one with 1 over Q, otherwise you don't have the matching. So this is a good check that you indeed have one copy that is deformed with Q and one with 1 over Q. So the two S matrices are not related by one particle change of basis, but as expected, they are related by a twist. So, and this is the explicit form of this twist in the fundamental representation. So here your phi1 and phi2 are the doublet under an SU2, and psi3 and psi4 are the other doublet under SU2. And the only case in which this twist is non-zero is when it acts on these states. And here you see that the braiding appears as expected, and also you have the representation parameters that appear. Okay, so we have learned, so this was for ADS5 crosses 5. So we have constructed the different Q-deformed S matrices, and they are related by this twist. So now let us look at the deformations of ADS3 cross S3 cross D4. So in this case, the symmetry breaking pattern is the following. So this was already in the previous talk. So you have your two copies of PSU1, 1/2, and the remaining symmetry algebra after Lycon gauge fixing and going off shell is SU1, SU1/1. You have 4 copies of those, and you also have a central extension. Now in the Q-deformed case, your two PSU1, 1/2 copies are Q-deformed, and so are the SU1/1 copies. So here you have, again, so you can have a 2-parameter deformation, and therefore you can also have, so the quantum symmetry will be will have 2 parameters, Q left and Q right. So Q left will tell you the deformation in the left copy, and Q right is the parameter for the right copy. So again, we can have different Dynkin diagrams, so different quantum groups for PSU1, 1/2 that are based on these different Dynkin diagrams. So here I will restrict to the case in which I take the same Dynkin diagram is in both copies. So you can have these 3 different scenarios. And in this case, since SU1/1 is actually rank 1 superalgebra, you only have one type of Dynkin diagram. So in this case, you actually expect the exact S matrix to be the same for all these deformations. This 2-parameter deformed S matrix has actually been constructed by Ben Hoare in 2014, and with Stijn and Yannik, we checked that the three-level expansion matches with calculations from perturbation theory. So all these different eta deformations have the same three-level S matrix up to one particle change of basis. So this is in contrast with the ADS5 cross S5 case, where we had different S matrices that are related by a twist. Here we only have one S matrix, and this is because the superalgebra that you end up with after Lycon gauge fixing is of minimal rank. So you actually only have one type of Dynkin diagram, so you can only construct one exact S matrix. So now let me conclude and also present some open problems. So what have we learned during this talk? So first we have learned that a good way to generate new integrable theories is to look at integrable deformations. So you start, so these will be deformations of your original integrable theory that preserve this property. The example that I focused on during this talk are eta deformations that are conjectured to correspond to Q deformations. So the symmetry algebra of your undeformed theory will be promoted to a quantum group. So in this case, Drinfel'd type quantum group. And we have also learned that eta deformations of superstrings, or equivalently Q deformations of superalgebras, they are not unique. Namely, they are classified by the Dynkin diagram that you choose for the undeformed symmetry algebra. We have also seen that not all of them will solve the supergravity equations of motion. And if you want to have a good interpretation of these eta deformations in the context of string theory, you need to look at a specific type of eta deformation that is based on this fermionic Dynkin diagram. We have also seen that you can actually use the Q-deformed symmetry in order to bootstrap the exact S matrices, these exact worldsheet S matrices. We have seen that in the case of ADS5 cross S5, these different theories will actually have different S matrices, but they're related by a twist, a Drinfel'd twist. We have checked that this exact Q-deformed S matrix, so the expansion thereof, matches with perturbative calculations. And we have checked also that so since the S matrix that you bootstrapped using the symmetries satisfies the quantum Yang-Baxter equation, you have a compatibility with integrability. So there are still some open problems. So one open problem is to understand how this twist affects physical observables. So maybe something that I didn't mention is that the beta equations and the thermodynamic beta ansatz and quantum spectral curves, so these have all been constructed in the Q-deformed case, but the construction was using the distinguished S matrix by Bezert and Kotev, and it is not clear whether, it would be interesting to find the beta equations in the case of this fermionic S matrix. Then another open problem is, perhaps I add one, which is to find the deformed dressing factors in the case of ADS3 cross S3 cross T4. So because here we bootstrapped using the symmetries, but you still have these dressing factors that are unknown. So it would be interesting to know what is their explicit form in the Q-deformed case. Then another point is to better understand the Weil anomaly that appears in these eta deformations. So for those that are not solutions to the supergravity equations of motion, something that I didn't expand upon is that these theories have kappa symmetry, and therefore they satisfy a set of generalized supergravity equations of motion. And there is ongoing progress in order to make sense of these theories in the context of string theory. Another point is the connection between eta and lambda deformations. So as I have highlighted during the talk, these eta deformations correspond to quantum deformations, but with Q being real, and this lambda deformation actually have Q being a root of unity. And there exists a relation between these two theories that is called Poisson-Lie duality. But for the moment, I think that only one lambda deformation is known in the super case. And here we have seen that we can have these different eta deformations. So it would be interesting to know whether we can actually have different types of lambda deformations as well. And a broader question is the interpretations of these Q deformations in the context of holography. So remember that all this talk was based on a deformation of the string side of the duality, and it would be interesting to understand better something about the dual. And progress has been made in the case of So not Q deformations, but in the case of homogeneous Yang-Baxter deformation, where there is some relation with non-commutative field theories. But in the case of Q deformations, it's still an open problem to have an interpretation in the context of holography. So thank you for the attention.
Questions?
I have a couple of questions. One is a little bit technical. So if you go back to the slide for ADS3 where you were discussing the pattern, yeah.
Yep.
So why don't you have a 1/QL and 1/QR right here?
Sorry, yes, I was a bit sloppy in this slide because of space problems. Oh, okay. But in theory, you also have you have this copy that is explicitly written down that is deformed with Q left and Q right. And then you would have another copy that presumably is deformed with 1/Q left and 1/Q right. So the subtlety here is that actually you have a symmetry when you exchange Q left to Q left inverse or Q right to Q right inverse. So in fact, it will not matter in the end. So,
but it does in ADS5.
So in the case of ADS5, there is a difference between the distinguished Dynkin diagram, where you also have a symmetry Q going to Q inverse. So again, there you don't see anything. However, for the fermionic case, this Q to Q inverse is no longer a symmetry, and you see a difference. And if you want to match with the perturbative results, then you need to take Q and 1/Q. So this is a good indication that indeed you have this 1/Q in the second copy. But yeah, in the distinguished case, you don't see it because you have this symmetry.
And maybe very briefly, maybe more conceptual question. If you go back to Q in terms of T and eta.
Yes.
So if I take that relation seriously, which is semi-classical, but let's say that I believe it more generally, could I sort of believe that I can do some sort of weakly coupled limiting the gauge theory, something like T to 0, which still remains deformed, and work out some like one loop spin chain that still has this symmetry or some limit of this symmetry. Could that make sense?
Okay. So let me understand. You want to take this and take the T going to.
Let's say that T goes to 0, but the stuff inside remains finite because also eta goes to 0. Could that be something that makes sense to study, like in some weakly coupled Yang-Mills?
So to be honest, this is a very interesting question, and I'm sorry I cannot answer.
We have a question on Zoom.
Yeah, Fiona, maybe let me elaborate one more time, maybe to make this precise. When you, so just to make it clear, we have this semi-classical Klimchuk proposal of the Yang-Baxter deformation, the functionals that you are showing. Then we have Benoit and people defined as single Q deformation, and Ben is has generalized this to 2 deformation. Principal one can do 3 and 4. But when you talk about this 2-parameter deformation and before the Q deformations, you talk about the cases of the Dynkin diagrams which solve Sugra equations and the ones which don't solve, and the last one which is fully fermionic, which does solve, which is supported by 3 and 5 form flux. I'm just wondering if this Q deforming argument, does it affect if I proceed, for example, with Ben, the 2-parameter deformation, and which is doubly deformed Q doubly deformed R matrix. This argument affects this. You can construct analogous diagrams, and you have still this argument that the separated one, mixed one, do not solve Sugra equations, and the fully fermionic one. So the Q deformation, does it affect this Sugra equation solving argument or not? The Q
so do I understand correctly that you ask whether in the 2-parameter case you also have this pattern of not being supergravity?
Right. For example.
Yes. Okay. So there is a general constraint on this operator R that it should satisfy in order for the theory to be for the background to be a supergravity solution. And I mean, it also works, this argument also works when you have, it seems to also work when you have two copies and if you deform them in different ways. So
Yeah,
if you have these two deformation Q left and Q right.
Yeah, I see. Also, there is, yeah, as you know, probably there is this caveat which is interesting, that actually in Ben's case, single one of the Q parameters could be reabsorbed into the, how they call them, this representation characteristic parameters. So essentially, which would lead to the single deformation. And this is not the same that taking one of the Q parameters to reproduce Benoit and other people single deformation result. So I'm just wondering, yeah, but that's a separate question. If this also works for you. And maybe one more, if I'm allowed, a quick question on this Poisson-Lie dual. Just a very basic point. As you say, if we think that this Poisson-Lie transformation, Poisson-Lie duality holds, as you say, we have just one example of the lambda deformation, but I pick up one of the eta deformations. Is it possible through this to generate out of this one, by using Poisson-Lie duality, to generate the, say, conjectured lambda deformation and check if obtained lambda deformation is integrable from the many known etas, for example, as you mentioned?
Yeah, for Poisson-Lie duality, one thing that you can do is that you have explicit formulas for the Poisson-Lie dual sigma models. So you can just plug into your dual formula, that would be for the lambda deformation. You can just plug in the different R matrices, so these different operators R, and you can then check whether the results are the same or whether they are different. A subtlety is that this Poisson-Lie duality will actually map you from eta deformations to not exactly lambda deformations, but analytic continuation thereof. So one thing that could happen is that you actually have different lambda star, like these analytic continuations. You have different analytic continuations of the lambda model, but the lambda model itself is unique. Or so, yeah, I mean, you can do that. You can use this formula for the explicit formula for the Poisson-Lie dual model, and you can plug in the different operators R and see whether the theories are the same or not.
Right. Yeah, I'm just wondering exactly what is the subtlety and the, okay, I see. In principle, okay, good.
So we have also a question in the chat. What about the case of 3-parameter deformation, B, Yang-Baxter, and flux? Do you think it is also true that full fermionic Dynkin diagram is associated to solving Sugra equations?
Yeah, so very good. So in the ADS3 cross S3 cross T4 case, you can have a 3-parameter deformation where you also have one parameter that controls the amount of NS and S flux. And in this case, I do expect that when you consider the fully fermionic Dynkin diagram, you also obtain a background that is a supergravity solution, but this still needs to be checked. So obtaining these backgrounds is usually a difficult problem, and yes, it would be interesting to find the fluxes for this scenario and check that this is indeed the case. But I do expect that indeed, when you take the fully fermionic Dynkin diagram, you obtain a background that solves the supergravity equations of motion. But this still needs to be checked.